Hey there, Professor, look what I brought. Now tell me what's my rock.
Hey there, Rockhounds. Welcome to another episode of What's My Rock. I'm your geology professor, Dr. Abstract. I'm here with my new friend, Austin.
Mm-hmm.
Would you tell us where you live, please?
Like exactly the address?
No, not the address.
Joking.
Well, you this
No,
video,
I
people
know.
will come. You might have fans after this. You
Maybe,
never
it's
know.
possible. I live in Moore Park. I teach in Oak Park at a high school.
Okay.
I teach physics and engineering.
So you're a pretty nerdy guy then. You like science and you teach physics. And
Yeah.
I say nerdy and affectionately, of course. You realize.
No, I appreciate that.
Yeah. How did you get into rocks?
I mean, as a kid, I was into rocks.
Okay.
Just naturally always looking at the ground and, pick up things.
Mm-hmm.
I wasn't much into rocks until a little bit later in my life. My grandfather was a chemist who collected many, many minerals.
Mm-hmm.
I was going to go on a camping trip, and I bought a UV light because I wanted to hunt for scorpions.
Okay.
And so I was like, hey, I shine some of these on these minerals. Mm-hmm. And so I, shining my UV black light on some minerals, and lo and behold, some of them glow. And I thought that was the coolest thing ever.
So UV fluorescence was your gateway drug?
Yes.
Okay, got it.
I've been starting to use minerals and stuff in like my teaching lessons.
Mm-hmm.
So when we talk about optics and we talk about modern physics and like electron levels, I bring up my fluorescent minerals.
Great.
When I talk about polarization, I have, minerals that interact with light with polarization differently, like iolite and calcite, a lot of stuff like that. Thin film interference, there's cool minerals like rainbow obsidian, fire agate. For things like diffraction, I have things like iris agate, where if you shine a light through it, it'll show a diffraction pattern.
Oh, I didn't even know that. That's cool.
Yeah, if you get it thin enough and you get the right kind, you can get a nice diffraction pattern. It's just like a diffraction grating.
Okay, but you got to get it as thin as the wavelength of light, presumably.
Well, the sample itself doesn't have to be that thin. It's just the agate bands have to be on the order of magnitude of wavelength.
Well, what do you got for us today?
I've got 3 different rocks. One of them is a fluorescent that I have asked people about. No one really knows.
So let's look at it. So it's actually kind of have a lower density than you might think, even though it kind of looks very shiny, almost like it would be made out of metal. And it has these really interesting elongate crystals. We would call them acicular crystals, if you've ever heard of that word before. It's okay if you haven't. Nobody has. This means needle-like.
Yeah.
And they're growing on the outside of this thing. It looks more granular on the inside. This is a weird rock, Austin.
I agree.
Where did you find it?
So I didn't find that one. That was in my grandfather's collection. That was one of the very first rocks that I shined a black light on, and I was like, wow, this one glows for a very long time with a very pretty color.
There's these elongate crystals. They're actually beautiful crystals when you look at it with a hand lens. My first inclination is that this is not a natural material. Do you think this is a natural material, or you have no context whatsoever?
Like, I know, there's always slag thrown around here and there.
Yeah.
And I wouldn't be surprised. I mean, because my grandfather had some non-natural minerals in his collection.
Slag usually doesn't have these really beautiful elongate crystals.
Yeah.
A slag is usually a totally melted material. This is like a weird combination of like melted and crystallized. And like a slag wouldn't have a lot of crystals in it usually.
Because it's fast cooling.
Because it's pretty fast cooling and it's pretty mixed up. Exactly. That's that kind of a thing. I guess it could. It depends on what the crystals is. I mean, this could be some kind of weird flux material. Flux is a material that you're not interested in, that you put it in. It either helps the melting process, or maybe it helps extract some sort of chemicals that you want to extract. But those things can be like weird salts and things like that. Who knows what they are? So could these be like crystallized salts or something? But they're pretty hard. If they were salts, they would break pretty easily. So this surface right here is a sort of a silvery gray shininess to it. And I mean, in nature, usually when you get something that's shiny like this on the outside, it's usually some kind of a glass. And that would be something like, like some kind of volcanic rock, usually, like a like scoria or something, some basaltic glass. That's a frothy kind of basaltic glass. For that, I would want to see a lot of vesicles, which are little air bubbles in it, but I don't see air bubbles in here at all. If all I saw were the inside, I would look at this and I'd be like, this kind of looks like a bunch of grains of, maybe a sandstone or, some kind of quartzite or something, I don't know. But it looks granular inside. And then to have this sort of melted thing on the outside is really odd. For it to be a natural material. I'm not going to rule out that it's a natural material. So maybe we should get a little compositional information on this, because that might help us figure out what's going on. So we'll break out the old XRF. Okay, is that cool?
Sure.
All right.
Sounds good.
Okay, so let's put that here. We're going to we can analyze. Okay, so let's press start. So look, we got 20% calcium. So calcium is a pretty big number.
Interesting.
So we're getting calcium, just a sniff of 0.2% potassium, 0.3% sulfur, a whole bunch of trace things, scandium.
How often
Okay, here we go. Aluminum. Okay, a little bit of silicon, not much silicon. So this is what we get. We get 20% calcium, 15% aluminum, 2% silicon, and the balance is 61%. So that's going to be anything fluorine or lower, which is almost always going to be oxygen, carbon, hydrogen, things like that. And so our main cations are calcium and aluminum. I'm a little perplexed at this one. Let's try a little acid test, and if it fizzes, that'll tell us there's a little calcite in there, and that wouldn't be a weird thing to see industrially. I'm going to try to put it like right there.
But yeah, I think it is fizzing. Yeah, I do see bubbles.
Yep. I see it too. So there's probably some calcium carbonate in there. It can be mixed in with whatever the aluminum is. What in the world are these long pieces here? I want to get one more look. I'm just trying to get a view of the shape of the prism. So I teach a mineralogy class, and we spend a lot of time talking about crystallography, which is the shape of crystals. Some like quartz is hexagonal. Other crystals are not hexagonal. I don't think these crystals are hexagonal. I think they're actually they kind of look like this to me. They either look like that or they look like that. Like this is the cross section, right? I don't think it's quartz for sure, but there's not enough silicon in there for it to be quartz. So I'm going to give you sort of the best I can do with this right now. First of all, the composition is very unusual. Like if this were volcanic, just having 20% calcium, a little bit of aluminum, a little bit of silicon, that's pretty unusual. There's only one kind of volcanic rock in the world that's like that, and that would be a carbonatite, which is there are these really unusual, pretty rare lavas that are made from mostly calcium carbonate and some silicate minerals, but there's no bubbles in it. The other thing is this thing is very crystalline. Most lavas are not completely crystalline, so I think this is not a lava. So if it were a lava, it would almost certainly have some glass in it or some really fine-grained stuff, and it might have little crystals floating in it. And so I don't see that. When I look in here, everything is completely crystalline, and only this surface is glassy. So that to me just doesn't feel like a natural material, but I'm going to propose something. We could try to do X-ray diffraction. We need to identify what these minerals are, and but that's a destructive technique, so we'd have to take a little chip off. Would you be willing to take a chip off?
That's fine.
Okay. Let's put this aside, and let's see what the other ones are.
Sure. So I have this one. This one I did find, so we know this one is natural.
Okay.
Hopefully. This one is Santa Monica Mountains.
Let me try to scratch it. I don't want to break it, though. It's a pretty small piece, so is that okay if I scratch it? Do you mind?
Sure.
I mean, I don't want to ruin it. Okay. When I'm looking at this, I'm definitely seeing streaks of metal.
Okay, so it's hard.
This is a hardness of at least probably 6 or higher. The most obvious thing is that this would be quartz. There's no cleavage to it. It's sort of like a little bit clear, sort of an eroded piece of a botryoidal chalcedony or agate, something like that. And I know, since I've been there to the Santa Monica Mountains, I know that there is some blobby botryoidal quartz that's up there. Another possibility, though, is this could be something, some weird mineral called a zeolite. And of course, I have to check the hardness on that. But there's these little crystals that grow in pockets, air bubbles in volcanic rocks. And there's some volcanoes that shoot through the Santa Monica Mountains, some dikes and things like that. Not giant volcanoes, but there was a lot of volcanic activity in Southern California like 20 million years ago. And so there could be zeolites that are growing inside these volcanic rocks, and maybe one of them popped out and weathered. That's a possibility. I think the first thing we're going to do, let's test the hypothesis that this is just quartz, okay? And we'll run it through this thing, and if all we get back is silicon, then it's either going to be quartz or amorphous silica, one of those two things, okay? So let's go ahead and try that out. Silicon, there we go. Yep. 43% silicon. By far the most abundant cation in there. So again, let's review. We've got, it's harder than metal. It's sort of a little bit translucent gray. It doesn't have any cleavage to it, meaning it doesn't have any flat surfaces that appear to be breaking. And finally, it has this crystal habit that looks like these radiating features, but is actually a slice of botryoidal quartz, of sort of a blobby, like chalcedony kind of a thing. And then, of course, this got eroded somehow. Like this has been tossing around. Maybe it got tossed around in a stream or something for a little bit. But I think this is almost certainly going to be quartz.
All right.
Okay. Sound good?
Yeah.
Okay. Right. So that's my opinion on that one. Let's see
Cool.
what you got. One more?
One last one. This one right here, it just has a weird optical effect to it where like it kind of looks purple, but it doesn't. I don't know how to describe it.
Okay, this one, yeah, no, it's got some purple in it, and it's got some clearness to it. This to me looks like the mineral fluorite.
Okay.
Now fluorite is famous for having fabulous cleavage, right? And so I'm going to look to see if this mineral has cleavage. Okay, so I'm looking here, and I can see little layers that are in there. Yeah, that looks like stacks of paper put together. So this looks like very much like there's cleavage in there. Now, a test is that this, fluorite has a hardness of 4. The question is, do we want to try to scratch this? And maybe you like the specimen, maybe you don't want to scratch it.
I'd prefer not to scratch it.
Okay. Now, we can do a chemical. If you don't want to do a hardness test, we could go back to our good old friend, the XRF. We should call this the XRF show. But the truth is that the chemistry would be a pretty straightforward test because the composition of fluorite is CaF2, so calcium difluoride. So it won't see the fluoride. But in this case, using XRF will give us a test to see if there's a lot of calcium and nothing else that that'll detect. So that's a non-destructive. So we won't destroy the pretty crystal, but we'll just do XRF. I would irradiate myself if I did it like this. Although I have had my kids already. Okay, I think that'll work. Let's see if I put it like that. It just needs to hold. There we go. All right. Science. Scotch tape and mineralogy. Okay, so drum roll, please. Look at that. Calcium.
Yep.
Boom. Okay, big calcium signal.
Yeah, it says
57% calcium, 42% balance. Again, we've got cleavage, we've got crystal form, which is cubic. We've got the color, and I don't like to use color by itself, but fluorite is commonly purple and clear. That's a very common fluorite color. I didn't even ask where you found it. Did you find it, or was it?
That was another just specimen from my grandfather.
Got it. Okay. And we have a composition that is dominated by calcium. I'm happy with this being fluorite. So how do you feel about that?
Yeah, I think that's a good assessment.
All right, and that was what you suspected, right?
Yeah, that was my first guess.
All right, good. So the last thing, we just haven't figured out what to do with this thing.
Yeah.
This technique called X-ray diffraction requires powdering a sample.
Very fine. Very
fine. As fine as we can get it. And so we don't need a lot. We just need like a pinky finger's worth of it. Okay?
Yeah.
And so what we're going to do is you'll chip off this little bit here. And then in the follow-up video or something, I'll X-ray that and see if we can get to the bottom of this. For the record, I don't think this is gonna be natural, but we'll just see. We need a little bit more information about what these are. It could be something really exotic, and if it came from your grandpa's collection, maybe he did get something really exotic.
All right.
So go ahead and clip that off. And you got glasses on, so we'll use those as safety goggles.
Squints.
Just, you don't have to hit it too hard. Do it. Chip it gently at first.
There we go.
Perfect. We'll take all.
There's some powder right there.
Yeah, that's right. So we'll take all these little bits here.
It smells weird. Do you smell that? Maybe we shouldn't be breathing that in.
Yeah, that's true. We don't know what it is. Breathe it in. Thank you.
Could lick it.
You could lick it. We didn't sign a waiver for licking rocks.
Yeah.
Okay, so we'll take this, and I'm going to put that aside. Let's wrap it up. Once you get the other friends out, we got that one, and the fluorite. Yeah, we got to take it off of our.
Almost left it here.
That's right. No, that would have been bad. Okay, this little guy here. The XRF came back dominated by silicon, and the other characteristics I think are consistent with it being a little chunk of botryoidal or some sort of vein silica material. I'm calling it silica. Silica, geologists use that as sort of like a vague term, meaning anything that has a composition of silicon dioxide, SiO2. Usually it's quartz, but it can be something that's not quartz, that's not even crystalline. So it could be what we call amorphous silica. It's probably going to be quartz though, eroded from a botryoidal vein of some kind. Okay, and then we've got this fluorite, which is, it's got purple and clear zones in it. Microscopically, I can see cleavage in there. And the edges of this crystal are 90 degrees, which is what you'd expect for fluorite, which crystallizes in the cubic crystal system. And the composition is dominated by calcium, which is what we'd expect for an XRF analysis. So the best explanation for this is really fluorite. So I'm happy with that being fluorite. Now this bad boy here, again, it has a surface that looks like it's melted. Simultaneously, there are these big crystals that are growing out of it. The middle part of it doesn't look like that at all. It looks completely granular. The composition of this is calcium and aluminum, basically, with just a sniff of silicon, which there could be a little bit of silica in there somewhere. But mostly it's a calcium, aluminum, plus the balance, which could be oxygen, hydrogen, carbonate, whatever. It fizzed a little bit.
It did, yeah.
So some of that calcium could be calcite in there. But even so, the composition is extremely unusual for a natural material. So all those things together, the fact that there's no bubbles in there, the glassiness doesn't penetrate the whole material, as I would expect for a volcanic rock. The fact that the composition is very unusual. I'm going to say this is some sort of a human-made material. I have no idea what it is. It's really cool, though. It's got these really beautiful crystals there. The crystals I don't think are quartz. I don't know what they are, but I'll do a follow-up analysis using the X-ray diffraction, and that'll tell us what crystals are in here. My money is going to be on a human-made material for that one. Okay.
All right.
And not a meteorite. How do you feel about all that?
Yeah, it's very cool.
All right.
Yeah.
Good. Well,
Glad I came.
Good. Come back and get your master's in geology.
You're tempting me, but I've got 2 kids now and a job. And
okay. Well, maybe they'll come get their master's in geology.
We got a bunch of rocks. I'll encourage them.
It's all good. You can just like rocks. You don't have to go get a degree in it.
Yeah.
You can just enjoy them. Maybe that's for the best.
Yeah.
All right. So you're off to a gem club or something, right?
Yep.
All right.
Giving a talk on fluorescent minerals.
All right.
Yeah.
Well, you'll talk about willemite and franklinite and wollastonite, calcite, all those things. So enjoy, and thanks for coming to visit.
Yeah. Thanks for having me.
Thanks for coming down. Okay, so we're gonna do an X-ray diffraction analysis of Austin's weird rock, and I have the little nuggets that he left us. He's no longer here. He went home. But in order to do X-ray diffraction, we have to turn this rock into a powder. We're going to use something called a shatterbox, which is this shaker that's going to shake this thing inside a tungsten carbide cylinder and it's going to pulverize this thing to bits. So we're going to open this up. There's a ring and this little cylinder in it. And what happens is when the thing moves, we're going to shake this thing violently in the machine, and these little pieces are going to flop back and forth, and they're going to turn Austin's weird rock into a pulverized powder. Put this back on. Make sure it's set, and it is. Put it in there. We're going to close it up. And we're going to press start, and the thing's going to start vibrating. Okay, so you can see it's still moving in there. See that? It kind of moves around. All right, so let's open it up. Let's see what we got. Oh my goodness. Look at that, all that white powder. So we're gonna scrape all this. Hope it doesn't get identified as something really hazardous and toxic. Definitely has a good sulfur. Plastic cup, like a little Jello shot cup. And we're gonna put it in there. And I'm going to wipe it off and go wash my hands because I'm not sure what this stuff is, and that's probably stupid for me to be doing this, but I'm a geologist and we don't have any fear. All right, see that? It says caution, X-rays. That's because we're standing in front of an X-ray diffractometer. I'm going to call it XRD for short because that's what all the cool kids say, XRD. It's not XRF, X-ray fluorescence. That's the little gun that we use in analyzing chemical compositions. If we put something in here, it's going to say you have quartz or you have calcite. If we use XRF, it's going to say you have calcium or silicon. See the difference? So calcium, silicon are elements, quartz, calcite are minerals. This actually identifies minerals. And the way it does it, it's going to shoot X-rays into our powder, and the X-rays are going to interact with the crystalline structure of the minerals. And those X-rays are then going to leave the mineral. When we get a really strong signal, we're going to note what angle that signal is, and that's going to help us identify the minerals. And it gives us sort of like a UPC barcode that we call an X-ray diffractogram. Come on in here. I'll just show you how the machine works. So right over here, this is an X-ray tube. It's going to shoot X-rays out of here, and it's going to hit our sample, which we haven't put it there yet, but we will. And then this machine over here, this part over here is going to count X-rays. And as the experiment runs, this thing's going to move like this, and this thing's going to move like this, and we're going to change the angle. And every angle that we get a strong measurement, we're going to make a note of that angle. And that's the simplest way I can describe it for you, YouTube. First, what we have to do is we have to prepare our slide, which we're going to do right over here. We're going to take this out. I'm going to put it right in here. Like that, that's plenty. See, we got more than enough. Put that right there. And I'm gonna sort of smooth it out a little bit. First, I'm gonna break it up. Don't get too excited here. I learned how to do this in grad school. All right, and now what I'm gonna do is I'm gonna wipe this off. I'm gonna take another slide and just sort of press down on that. Got my slide. Right in here. Okay, so the sample's in, and I'm gonna start the analysis, and it's gonna take about 5 minutes, but we'll speed it up for the video. So I'm gonna click run. We're gonna watch the data come through. This red line right there, this is our data. So this is our graph. The graph on the x-axis here is that angle. We call it 2 theta, don't worry about that. It's called 2 theta. On the y-axis here, this is the intensity of the x-rays that are coming out. And at certain angles, we're going to see some beautiful peaks, and we're going to use those peaks to determine what the mineral is. It's starting to move over there, Dylan?
Yeah, it's moving. Very subtly.
Okay, there's our first peak. So not a very impressive peak. Nothing to write home about. Hopefully we'll get bigger ones, but that's about, this is about 15. Oh, there's a bigger peak right there. that peak came in at around maybe 18. Okay, so here we are. Here's our beautiful X-ray diffractogram showing all the peaks of whatever minerals are in there. What we're going to do, we're going to take this data to an older computer that has our mineral database on it. And that's the computer that's going to tell us what minerals are in here. And these are all the possibilities that it thinks it could be. So maybe I'm going to sort by chemical formula, and let's see what comes out that starts with calcium. Look at all these calcium aluminum oxides. So I found this calcium aluminum oxide here, and look at our diffractogram. See how that peak right there is also red, and this peak is red? This one is CaAl407, and that's in blue. So look over here though. Turns out that blue, there's a lot of things that can be explained by blue. So we're doing a good job here. Here's another formula for CaAl2O4. I'm gonna pull that up there. So we're basically explaining all of our peaks. They're either green, blue, or red, and all of them are calcium aluminum oxides. All right, let's do the recap with Dylan. Dylan, what do you think about Austin's rocks? Let's start with the weird one that we just analyzed using X-ray diffraction.
Yeah, that was a bit of a rabbit hole, and
Yes.
I will say, like, my bias being a volcanologist, when I heard the word carbonatite, I went down that rabbit hole a bit, and I went and, as you guys were discussing, I was looking pictures on Mindat, just because carbonatite's a very rare rock.
Mm-hmm.
And looking at it, as much as I wanted to be carbonatite, it didn't quite match some of the images I was seeing of carbonatites, and so it just didn't quite lean itself towards that.
Yeah, and I think you really need, carbonatite is a volcanic rock. I guess there can be intrusive carbonatites probably. But if it's a volcanic rock, it would need some kind of vesicles or some sort of volcanic texture. And I think that rock was completely granular, something that you wouldn't expect for a volcanic rock, even though the outside looked a little melted.
The XRD analysis that we did, that was kind of funky in a way on like some of those minerals we were coming up with. And
well, I mean, what's powerful is the combination of being able to go do the XRD and get a list of minerals, and then use the XRF analyses to say, it has to have calcium and aluminum and a little bit of silicon in it. And that helps us narrow down the tremendous amount of minerals that the computer thinks could be in there, right?
mm-hmm.
And so that's a really nice illustration of how to combine these powerful tools. So all you need is $50,000 for the XRF, $600,000 for the XRD. So, you know. And the minerals that we found, the internet told me that they exist in meteorites, but they're going to be really, really small microscopic grains, and they're not going to take up the entire rock, right? So these calcium aluminate minerals that are granular, that comprise an entire rock, that has to be an industrial product. You know, the main minerals were CaAl2O4 and CaAl407. Those compositions are consistent with cement minerals. So there's a whole literature on concrete engineering and material science that's related to what we call cementitious minerals. When I went to Wikipedia, the very first image at the top of the calcium aluminate entry is a phase diagram of calcium aluminates, and it turns out that there's a field that contains CaAl2O4 plus CaAl407, so they coexist stably in that thermodynamic system. So which means that, you know, if you dial in the right composition, you can synthesize those two minerals. So I think that's what happened, is there's some company that makes concrete additives, and somehow a chunk of their product fell off of a truck. Speaking of falling off of a truck, I don't know if you knew that I used to work in a concrete testing facility in upstate New York.
That's new to me.
Yeah. It was in Ossining, New York, which is about a couple blocks from Sing Sing prison, where they used to put all the old mafia guys. So,
Oh, okay.
and we used to have to regularly go test concrete at plants operated by guys named Vito and Vinny. For real, this is real. So I know a little bit about the concrete and cement world scientifically. So yeah, and in these cements they have calcium, aluminum, minerals. So our nose, which is a good detector, detected sulfur. Mm-hmm. I did a little sleuthing on the interweb, and I forgot about this mineral called ettringite. And ettringite is a mineral that can occur in concrete. It also occurs naturally in hydrothermally altered rocks and other settings like that, but it does occur in concrete as well. And its composition is calcium, aluminum, and a little bit of sulfur. So I think what we had is there's a trace amount of this ettringite, and the other piece of evidence for that is that the crystal system of ettringite is trigonal. You know, remember I drew out those sort of stretched hexagonal cross sections for Austin, and I'll be darned if I didn't find crystals on the internet that had the exact same morphology to them, the same crystallography, as we would call it. So I'm feeling pretty good about ettringite being an explanation for those long crystals, even though we didn't see it in the XRD because there probably wasn't enough to show up. So calcium illuminates, and those ettringite crystals, all of them are synthetic. It's an industrial material. It's almost certainly going to be a concrete additive, so I'm feeling pretty good about that. So anyway, so Austin, there you go, concrete additives. So you're in the concrete business now. So have fun with your new rock. Any last words on that one?
That was a fun rabbit hole to go down.
It was fun.
We had a lot of fun with that.
And then his other rocks, the fluorite.
Fluorite. Yeah, so when I first saw that, it was like first things first. Fluorite, I've seen purple varieties. I've also seen amethyst, which is, of course, purple variety of quartz. And of the two, it had a much more kind of geometric shape as fluorite, especially like that 90-degree angle.
And once we saw the XRF, that showed that it was dominated by calcium, with the fluoride being undetectable. There's really no other reasonable explanation unless it's something really obscure, fine. Yeah. But I mean, let's say 99.99% that's fluorite. Mm-hmm. Okay, and what about his last rock, that little quartz nugget?
Quartz nugget. I was thinking possibly quartz when picking it up. Mm-hmm. I didn't do a hardness test at all when I handled it, but I mean, once you have done a bit of geology and you pick up minerals, sometimes you can roughly tell, like, this is a very soft mineral, this is a very hard mineral, and this kind of came out towards that very hard side. So, you know, like hard mineral that's common, quartz. I've seen quartz in all sorts of colors, including that one. Mm-hmm. And so its structure, not really any surprises to me. So
yep, I think that one's a open shut case as far as being quartz. Mm-hmm. Plus with the silicon being the only cation that showed up in the XRF. So that's a little chunk of quartz, very common. And there you go. So those were some fun rocks. Concrete additive is the highlight for me, even though it's not natural, but it was just fun. So last words about Austin's rocks.
Austin, you brought us a challenge, and hopefully we've fit up to it. It was quite something. So thank you for bringing that one in.
All right, and if you'd like to bring your rock to the show and be a guest, email us at whatsmyrock@yahoo.com. I'm Dr. Abstract. This is Dylan. Thanks for watching. We'll see you next time. Happy rockhounding.
Yeah, I've seen it all. That's why they call me a professional. I know you're proud of what you got, but this rock ain't worth diddly squat. I'm not saying that you'll never be wealthy, but this preoccupation doesn't seem healthy. Don't give up your day job, you better keep it a hobby on the weekend.